Right. Hello, everyone. Ciao a tutti. I'm going to be talking about IPIs. That's a follow-up with a previous presentation at LPC. So I'll be summarizing quickly what I was looking at. So I mostly care about isolated CPUs running with no hertz full in user space. So with no hertz, you have no hertz idle, where if you have a CPU that's idle, and we deem that it's going to be idle for long enough, we can turn off the tick. And then you can take that a bit further with, oh, if we have a CPU that's going to be running only in user space and not going to be doing any syscalls, we can also disable the tick in that case. So with CPU isolation, you can mostly solve like the scheduling issue of having interference by other tasks. So you only get you pretty much get only things that you put on those isolated CPUs, but you can still get interference in the form of IPIs. So that's not new data. That's exactly what I presented at LPC. In green, those are the housekeeping CPUs, and in red, the isolated CPUs. And those are just IPIs that you get over 20 minutes of running kernel compilation and some other random stuff on housekeeping CPUs, and then just like a nice user space task on the isolated no hertz full CPUs that never does a syscall. So we'd be hoping to be not seeing any red, but we are getting some. So we are getting some IPIs sent from the housekeeping CPUs to those isolated CPUs running no hertz full in user space, which isn't ideal. A reason for that, well, there's several. We do have some helpers to tell us, okay, our CPUs, like in the CPU mask, are isolated. We have some instrumentation to figure out if a CPU is in user space or not. It's just that we're not making a lot of, we're not using these a lot. The other side of this is it's also not that easy to reason about IPIs that you are sending out. Does it, like, should I be thinking really hard about which CPUs do I send that to? It's much easier to just say IPI, everyone solves my problem. In terms of what has happened since LPC, I've been working on the tracing side of things. So if you look at T+MP core, you now have actual trace points for IPIs being sent. We used to only have trace points for IPIs you received. So it was a bit difficult to figure out, oh, where did that come from? So I actually used that yesterday to debug some of the stuff I'm going to be talking about. So it's working. I do want to work a bit more on the ftrace side of things just for filtering, so that you can use the filtering mechanism to only get the trace events that are targeting certain CPUs. So you can directly filter the CPUs you care about, the ones that have no hertz full, that are isolated, and just get that. So it takes care of the post-processing for you. OK, so those IPIs that are hitting no hertz full isolated CPUs, what can we do about them? The ideal is we look, of course. So what I was seeing in this thing here, I was mostly instruction patching on x86, where whenever you start poking at the instruction, you then send a series of IPIs as you're doing it to flush the instruction context. And TLB flushes. I think I'll get to them a bit later. When I mentioned doing stuff with TLB flushes, Thomas really didn't like that. I need to do my homework and look at x86 TLB shootdowns and see like what we could do about it. But there's other IPIs that we can reason about already.
Oh. Yeah, when I was looking at this, isn't it true that like with TLB flush, you should have it happen in the hardware without having to send IPIs these days, or does that?
Not on x86.
Not on x86, and but you should only get a TLB flush IPI if there's really either if you have something where the MM is shared on the other CPU, so which is a sign of bad isolation, So if you have a process with hundreds of threads, and some of them are running on the isolated CPUs, and the other thread is on the housekeeping one, and
that's a broken
does
setup.
magic things and tears up memory and tears it down, then you get TLB flushes all over the place. But that's not a kernel problem.
That's broken as intended.
Yes, that's an implementation problem. A user space. The other one is, I don't know.
If kernel invalidates.
If kernel invalidates, right.
So
But-
kernel invalidates, you could make complicated and delay until the next
Entry,
kernel entry.
yes, you could.
The user invalidates, you cannot delay, and they are, as Thomas says, yeah, a design problem.
Yeah. You shot yourself in the foot.
Yeah, no, that's actually what I was looking at was
So
kernel
the
invalidation.
kernel ones, we might be able to defer them to next entry. Except for stuff like code patching, where you we have these cases where you install some trace point, watch point, BPF, whatever, and you allocate a trampoline page, and then you tear everything down. You can't delay because next entry might be too late. You might hit the stupid breakpoint already, and then jump into Nirvana land.
So, well, I'll get to some of the details a bit later, but if you do it early enough, you're supposed to be in non-instrumented regions, so you hopefully you shouldn't be able to hit.
Yes. If you do it really, really early on, it should work. Emphasis.
But that brings
emphasis
other
on
issues.
should.
For the applications freeing memory case, this is the vast majority of our TLB shoot downs. We use JE malloc. I don't know if it's the same for TC malloc, but our allocator is always trying to give memory back to the kernel to reduce its overhead, and the whole M-advise free path is one of the hottest paths in the kernel for us. Super expensive.
Right. So ideally, the best scenario is we reason about the use case, and we can realize that if the CPU is in user space, we could actually just not even bother with sending anything. There's been some recent discussion on synchronization for MMU gather by one of my colleagues, and it looks like we can just skip that CPU if it's in user space, and we don't lose functionality. Things work as intended. That's the ideal scenario. You have some other scenarios where you could skip the IPI, and yes, you lose functionality, but it's not critical. So anything that is about per CPU counter reading.
But any of those are not sensible in the first place. I mean, the CPU ID read should just die. Well, I mean, the issue is, and that's something we need to. It's on several to-do lists. So we should just do it once, the whole CPU ID read, cache it, and be done with it, and not.
Yeah, like you've done for APUF and MPUF.
Yeah. So because it doesn't make sense to do it over and over. The counters read on CPU, I don't know what it does.
I had a brief chat with Jonela, and it's not very relevant. I just found out by looking at the code, but it's
Okay.
not. The CPU ID read and some others, what I've been told is, problem is we have lots of user space just poking randomly at all of SysFS files to do like some logging and reporting. And it's not always actually that easy to get rid of all of this instrumentation, and it's causing IPIs, which is, it's a shame, but it's happening. So if we can, Marcelo Tosati was talking about that at LPC, if you can just do something like, we just make that fail, we don't send the IPI, and too bad you tried, but it happens that on the system we care more about not disturbing the isolated CPUs, we don't really care about this logging, so that's an approach. And the other category, and that's the one I'm interested in, I wish it didn't exist, but well, I have to take care of them, is callbacks sent via an IPI that we can't really skip. But if it only really affects the kernel and the targeted CPUs in user space, well, we could stash it somewhere, wait for the next user to kernel transition, and run it then. So we already briefly mentioned that for TLB shootdowns. The tools I've been working on, or well, using as test subjects, was instruction patching for x86, and the other one is something for ftrace, where you can do PID filtering for your events. So you have some work that happens at context switch because you are changing PIDs, but also if you are changing the list of PIDs, you send an IPI to all of the CPUs. Again, you can reason, oh, well, with ftrace, you're only going to get events in kernel space. So if you have CPUs in user space, you can just stash that somewhere and wait for the next user to kernel transition and do this update then. Before I get to that, I didn't really know where to put this bit, but I have to talk about it at some point, is how do we actually store the information we send with IPIs, so SMP call and friends. We, well, pretty much have a queue of callbacks, like a list we have per CPU, and the memory for the actual lists that are on there is just pre-allocated per CPU memory. So what this means is you have a storage depth of 1 callback per target CPU. So if you have back-to-back, for some reason, you have back-to-back SMP calls to the same CPU, the second one has to be serialized against the first one because you would be using the exact same list to store information. And that's perfectly fine because we are sending an IPI. IQ disabled section are supposed to be short and bounded, so it's going to get handled soon enough. If you want to apply this logic for deferring the IPIs, that falls apart because you are not sending any signal at all. That's the whole point. We want to keep the target CPU doing whatever it's doing. So you can't do any waiting of any sort like you would be doing here for deferring. So that's something I wanted to highlight because it's not necessarily obvious when you start looking at this. So we've already seen patches for that by Peter, where he used a bit mask as the storage mechanism for things that you have to do. And so you just have a bit to a callback mapping. So for instance, that one is for the instruction patching. Okay, so if you want to send IPIs for instruction patching, you still use the on each CPU's construct, but right now we already have something where you can also pass a predicate function which will filter the CPUs. And you hijack this predicate to first try to do some deferral storage. So you see, oh, is the target CPU actually in user space? Okay, I'm just going to atomically set this little bit and then not actually send an IPI. That works very well for this sort of callback. The problem is any sort of data you would want to pass. So if you have any sort of callback that you want to defer and that needs to work on some data pointer, which normally you have with SMP calls because you pass a function pointer and a data pointer.
Is there a specific example where you would need the actual data to be retained?
The ftrace thing I talked about is the example I'm using for that. There's a lot of others, but yeah, you'd have to pick one to work on or one that's relevant to you. For ftrace, we have to work on the actual trace array of the instance we're writing the or updating the PID list of.
Yeah, because if you stash that, you also run the risk that the storage that the pointer is pointing to is going to be invalid by the time you look at it.
Yeah, that's, well, I might just get to it. Because you cannot wait, the lifetime of the past data is problematic. Yeah. I think I've already rewritten that piece of code. Lorenzo, sorry. The thing on the right is some dirty hack I've done to try and make the lifetime work, but I've already rewritten that and it's...
Yeah, so basically you said that the issue
I can try. It's the, as I understand it, the instance for which you want to change the list of PIDs that are filtered.
Is there a way that you can do, for the one case, we just made a link list and added a like a piece of a list or something to do the instance array, trace array. So we actually, it does like this, just follow down and just trace array to execute against it.
Okay, so Steve's suggesting modifying the list of trace instances or having some sort of sentinel in there to figure out where we need to operate on. What happens if you want, or if you have to defer several instance modifications?
Yeah, so how about you just mark that CPU state as invalid and on entry, resync against some global state?
So the thing would be, what is the global state? At least in this scenario for ftrace, because you would have a list of PIDs filtered per instance that you've set up. I don't think there's a limit on how many instances you can set up. Or maybe. Where was I with that? Yeah, so if you want to try and play games like, oh, I'm going to allocate some data for that, you shouldn't go there, because Peter had a good point on that, which is if you have properly functioning no-hurtful applications that do stay in user space forever, this is essentially an ever-growing memory leak, or, well, unused memory. I hacked something around with the fixed size pool, but I really don't like it. So it kind of gives me the feeling this isn't like an approach we should be taking. The patches as they stand is very work in progress. That's also a reason why I haven't shared them yet. Well, I sort of got them in a shareable state on the flight to Ancona. So yeah, that's why I didn't send an RFC beforehand. But yeah, I have a mix of, so bitmask for coalescible, callbacks that don't really require the data pointer. That's the ideal, that's what we would want. But still a separate queue for those callbacks that require the data.
Yeah, I would try really, really hard to reconstruct stuff from global state. Like, don't rely on data. Just say that this CPU state is invalid, and then rebuild it.
Yeah, okay. So what, would you have something like a reconstruction step for every possible, every subsystem you'd think would need to be reconstructed, like for ftrace? I'm trying to think, what would you want to do then? Like, yeah, just have something saying, oh, actually just copy the state of some other CPU we know is in the same state and do that for ftrace and then potentially other things? Is that what you're suggesting?
Yeah, something like that.
Okay.
I mean, or just not trace no hertz full CPUs, but
I mean, you have to look at the IPIs per IPI anyway. So, and then you go and construct something in that subsystem, in that affected, where you say, this is the deferrable operations and whatever it takes, you can build up inside the subsystem infrastructure for state synchronization when it comes back into the kernel. Everything else is wishful thinking.
Yeah, I think copying some existing global state, that makes sense. Well,
Yeah,
I
mean, for example, the easy case is like text patching on x86. So
it's ideal because there's no data and it's idempotent. You can reach the IPI multiple times. It's not going to change anything.
And you come in and know you need to do a sync before you proceed. And you do it in a place where there can't be text patched reasonably unless except for the stupid mitigation crap, which can,
Who needs mitigations?
who needs mitigations, right? I mean, the other thing,
Yeah,
you
but the
don't
mitigation
know,
shit is done at boot.
pardon?
After boot, that doesn't change anymore.
Don't we have some static key crap which can change after boot?
I hope not. I don't know. I always try and forget all the mitigation shit as soon as possible.
Yeah, whatever. I mean, we have to look at it.
Yeah. Well,
It's just a matter of analysis, and it's not hard to find. I mean, if there are static keys which can change after boot, we have to think about where to put the synchronization points. But that's not hard. But the other thing I noticed, I mean, I understand that you stick it on context tracking, which means no it's full. I mean, in general, these kind of IPIs, as long as they are, for example, as text patching and all this kind of nonsense. So wouldn't it be smart to actually not interfere with user space, independent of no hertz?
So actually, yeah, I have, well, that's my last slide, but you can also reason about that with idle. So, well, Joel, you were sort of touching on that. Yeah, for instance, if you have instruction patching, maybe you don't have to wake up an idle CPU to patch it. You can wait for something actually important, an actual
not
wake-up
even,
source.
I mean, idle, but we can do a very, very simple and lightweight tracking of whether a CPU is out in user space or not.
no, that's actually really hard.
We have, so with context tracking, we are tracking that, but it's quite expensive. And I think we only do it for no hertz full CPUs.
It's only for, no, it's, I think we do.
You can force it, but it's more of a debug option than a.
Oh, whatever, yeah. Pardon? Yeah, for no hertz full. Right. RCU needs it for no hertz full. But we might need to think about whether we can do something interesting. And the NMI callbacks, I mean.
Yeah, so the things I have in there, it's for those callbacks that we are running in super early entry code. So if we go with the bitmask approach, we can reason about what really is running there. If we go with something a bit more generic, well, and a bit crazy, where you run any sort of SMP callback, then because that's in super early kernel entry, and you want that to be at the first user to kernel entry transition, you may end up having that code running in NMI and everything explodes. So yeah, what I'm trying to say is putting those callbacks in super early entry it solves some issues, but it can create more. So we have to reason hard about exactly which callbacks we put in there. I think another thing I was starting to ramble about was
the fun part with NMI is going to be if you have a string request pending due to text poke and you come in on NMI and do it early, you must do an IRET for syncing, and this re-enables NMIs.
cool.
No, we have code for that, so it's okay.
Okay.
But
Yeah, and it's NMI from user. Those are relatively easy. It's the NMI from kernel that's interesting.
yep.
Can you get, like, if you start going through the kernel entry code with a regular RQ, can you get an NMI on top of that?
Yes.
Okay.
The NMI nests, and then you can go into very dark corners of the kernel.
Yeah. Okay. Fine. I think one last thing I might add on that would have been, if you look at things like IQ work, we have this IQ work lazy thing where you don't send an IPI, you try and wait for the next tick to process the callback. Might be something worth thinking about for some of those other IPIs that don't necessarily need to be run super early in the entry code. Maybe we have something where we defer it a bit later on in the entry. And then, yeah, we don't have to think, or we have to think about it, but we don't have to consider this callback executing in NMI context. We can put it someplace that makes more sense. And I think you're, yep, Steve.
Okay, so I looked at the code and yeah, it's gonna be more complex than I thought. It needs to create state for each CPU and it does make sure it's running or not. And it has to be done within a mutex that's held. So we can't delay it unless we, well, we could make this is called from a sleepable context. If we were to delay it, that means it would delay the guy setting it until that CPU scheduled out. So that CPU is like running with no hertz full and just run forever. This would block forever.
Yeah, you're taking the CPU, calling CPU out. Yeah,
it would, because it has to be done before we release the mutex.
Yeah.
Now, if there was a way to say, the callback to say, hey, this is in user space, maybe we could do something on behalf of, like, just ignore that CPU, but then be able to say, because I think we can still do the work on behalf of the CPU that's running in user space, but this still needs to be done for that CPU. It's just that we need some sort of information saying this is in no hertz full. Here, run, do your check, whatever, and then continue. And that might be possible in this use case.
Okay, but then so you need to be careful about making sure that you won't have the target CPU re-entering kernel at the same time as you're trying to do the work for it. But I mean, we can.
Right, and it's only for this case, if it were to do a sched switch or something, it's fine, because like, say if it were to come out and we had a race condition where it just came out, when it came out, it would then do the update or the. I think I have to go back and look at the code, but we might be okay in that case. It's only the case where we haven't done a sched switch yet. It's forcing, yeah, on the sched switch, everything will update.
Yeah, yeah, but if you just have an IQ and no actual switch.
It's just the fact that we have to make sure the update happens before we return from this function call. So we don't care about races, before that. Once we release the mutex, then everything has to be synchronized once we release the mutex. So anything before we release the mutex, they could be updating. So we could just get a callback and do it on behalf. And if we missed it, we missed it. I think it's okay. I have to look a little more deeper in the code, but it's just synchronization. In this code, I remember I added it because I was, we were doing filtering of IDs and we're getting a lot of things. We were getting a lot of garbage out there because of this condition that we didn't want traced, and people were complaining about that.
Yeah, but then, so that would be the ideal where we don't even have to send the IPI. We can do the work locally. And
yes.
That would be.
But we have to have a way of knowing which CPUs.
Yeah.
Yeah.
Okay, thanks for looking at that. And yeah, that's all I have. So if there's no more comments or questions, early lunch.